Greetings, calculus students. Today we're going to begin the next unit, which is Unit 3, which is almost entirely composed of applications of derivatives. Now, before we get into it, just a little side note. I have spent the greater part of this evening going back through old papers, people doing corrections and things like that. So just a piece of information. I mean, I'm very grateful that everybody is so concerned about every point on an assignment being taken care of, that everybody is doing corrections. However, I'm noticing quite a trend on everything, and here is kind of the problem. I'm grading an assignment and getting it back to you guys, and we look at our paper and we see that we have a 96 on our paper, and we go, oh wait, I lost 4 points, let me find out where the 4 points went. So we get to studying the paper and we can't figure out where it is, and then we come up and we ask me, Mr. Hill, where are these other 4 points at, what's wrong with this problem? And we figure it out and we work it out and we do the corrections and we staple it together and we turn it in, and in the meantime we're neglecting our current paper trying to correct old papers, and then the result is we don't spend enough time on our current paper, and then that one comes in and that one has problems, and then we repeat this process over and over again. And unfortunately, some of you have demonstrated a bit of a trend where you are basically having to do corrections on every single assignment that we are doing, and unfortunately that is kind of making me have to grade 160, 170, 180% of the papers. And basically, like I said, I'm glad that we're so concerned about getting everything great, getting every single question correct. But what needs to happen is we need to be that concerned about getting every single question correct on the first submission, not having to turn everything in twice, because let's face it, the next level guys, they are not going to let you do corrections and turn things in twice. So we need to be more concerned with getting everything correct on the first effort, rather than relying on that corrections to be our safety blanket to get everything taken care of on the second try. So here in the second grading period, if I don't see an improvement on us getting things taken care of the first try rather than constantly doing corrections, then I'm afraid I'm going to have to change the correction policy, so that perhaps we can't get full credit back, or perhaps we cannot do corrections on grades that are over 70, things like that, and I really don't want to go down that road. So let's see if we can't pay a little bit more attention to what we're doing the first go round, and then we won't have to worry about what's happening the second go round. At any rate, section 3.1 is about Extrema. Okay, let's take a peek at our objectives for today. Your objective: the student will learn to determine the location of extrema within a function. I'm going to have you basically demonstrating, the student will demonstrate the ability to identify local maxima or minima and absolute maxima or minima within a function. Your essential question for the day is, do I know how to find the location of extrema? Okay, so let's take a look at this new topic of extrema. Now, we've been talking about the behavior of graphs as they approach certain points. And again, take notes as you see fit. A little bit of commentary here. Get down what you feel like you need to get down in order to understand. Okay. This idea of behavior of graphs as they approach certain point, it's been our discussion within, this has been what our discussion of limits and differentiation have been based upon. As you approach particular values, what exactly is the function doing? Okay. However, many discussions in calculus involve behavior along an interval as opposed to just at a singular point. Okay, so questions such as these become important in calculus discussions. Where is the function increasing at? Where is it decreasing at? Does it have a maximum value within this interval? Does it have a minimum value within this interval? Stuff like that are going to become critically important. The answer to these questions and more, plus the applications of these topics, is what we're going to be specifically focused upon in this chapter. Substitute. Anytime the students need more time to copy something down, please press pause in the video so that they can copy down what they need, and then press play when they're ready to move forward. Okay, extrema. Now here comes your typical calculus type definition. If a function f is defined on an interval I containing a value in the domain C, the function evaluated at C will be considered to be a minimum of the function in the interval if the function evaluated at C is less than or equal to the function itself for all x values within the interval. Now, when you get to thinking about what that actually just said, that makes perfect sense. That is more of a postulate than a theorem. That is just simply the way things are. Similarly, the function evaluated at C will be a maximum of the function within the interval if the function evaluated at C is greater than the function for all x values within the interval. Now, these minimum or maximum values are called extreme values or extrema of the function within the interval. They are also sometimes called absolute minimum or absolute maximums if the values are the lowest or highest for the entire function. And what that basically means is, let's consider the peaks of a graph. A graph may actually rise and then turn downward and then do this several times within a graph. So you may have 2 or 3 or more peaks within the graph, and one of them will be higher than the other ones. So the one that is higher is called an absolute maximum, whereas the other ones would be called local maximums, and the same idea applies to minimums. Okay, so note, it is not necessary for a function to have either a minimum or a maximum. Now, typically they do, it just depends on the type of a function. The following theorem is a guide for such information, and it's called the extreme value theorem. The extreme value theorem says if a function is continuous on a closed interval from A to B, then the function has both a minimum and a maximum on the interval. Now, 99% of the functions that we're going to be dealing with are continuous, okay, meaning they are not piecewise or anything like that, or if there are discontinuities within the graph, they are removable discontinuities within the graph, and we can end up with essentially what is a continuous function. So the function will have a min and a max on the interval if it is continuous within the closed interval from A to B. Okay, so let's take a look at an example here. Okay, here is a graph, and we're going to see if we can explore this idea of max and min. Probably not necessary for you to copy this guy down. Just please follow along visually and make sure that you understand the concept. Consider the closed interval from -5 to +2. Now, on this interval, there is no minimum recorded on that interval, since the function is discontinuous, approaching the minimum value. So it's quite clear that the graph does hit a trough in that particular location, but it's not considered to have a minimum value because the minimum value actually does not exist. Something fails in the function right there, and we have a discontinuity. On the other hand, there is a maximum within this interval, and it is located at 2, 3. The function is continuous, approaching that maximum value, and it is a closed interval, so the positive 2 in the domain is included as part of the function. So 2, 3 is part of the function, and it is a maximum value because it is the highest point within that interval. Now let's expand, or actually shift the interval to an open interval from -7 to -4. There is not a minimum value from -7 to -4 because it is an open interval, and that keeps the function from being continuous at the endpoints. So that goes against the definition that we just talked about. It has to be a closed interval. And it does have a maximum value. Maximum value is at -5, -1. An open interval where the function evaluated at C is a max, on open intervals where the function evaluated at C is a max, then the function evaluated at C is called a relative max of the function. Okay, so we already saw what would be going on in the closed intervals. Now we have the open interval. Similarly, on an open interval, where the function evaluated at C is a minimum, then f of C is a relative minimum of the function. So another way of thinking about these extrema is called local maxes and mins. And another way of thinking about that is just to say that they are the highest and lowest points within their immediate area of the function. Okay, so considering the previous graph once more, -5, -1 is a relative max, but not the absolute max of the function. And a moment ago we said that there was no relative minimum, or there was no absolute minimum at -7, -2 because of the discontinuity nature of the open interval. But at -7 there is a relative minimum because the interval is open. A telltale indicator of the exact location of a relative maximum or minimum will be that the slope of the tangent line at that point is 0. Now that's kind of a common sense statement there. It's basically saying that if the graph is turning from an increasing function to a decreasing function, that the tangent line at that location is going to be horizontal, and vice versa. If it's changing from being a decreasing function to an increasing function, once again, the tangent line is going to be horizontal. Obviously, the slopes of those tangent lines would be 0 at those locations. Okay, so let's take an example. Is the interval, is the point 3, 2 an extreme value of f of x? F of x is defined to be 9 times the quantity x squared - 3 divided by x cubed. Okay. Well, the derivative of this, because again, we are interested in knowing what the tangent line is doing at these particular, interested in knowing what the tangent line is doing for this function at different locations. Okay, so we'd have to find the derivative of this, and this is absolutely quotient rule, and it's chain rule within the quotient rule. And at the end of chain rule within the quotient rule, we would end up with this monster, and it would simplify down a little bit. And then ultimately what we would be interested in doing here is evaluating at 3, positive 2. So clearly what we would be doing here is we'd be taking all of the domain values out of the function and replacing them with 3. Okay, so plugging in, ultimately what we end up with is an expression that says 0/81. So the answer is 3, 2, an extreme value of this function. Well, what we have is we have a slope that is refusing to rise, but not refusing to rise, but running plenty. 0 rise, 81 run. Okay, so that is a horizontal line. We have a horizontal tangent line to our graph. Clearly, this is an extreme value of the graph. In cases where the function is defined at a particular value in the domain, and if the derivative of the function at that value in the domain is 0, or, should say if, right there, if the derivative of the function is undefined at that value, then C, wherever that is in the domain, is what we call a critical number of the function. Now, relative extrema occur only at critical numbers. Now, this is not to say that all critical numbers are going to be extrema, but all extrema will occur at critical numbers. Our guidelines for finding extrema on a closed interval are going to go something like this. And yes, I'm correcting every single slide on my typo that I have there. First step, find the critical numbers of the function in the open interval from a to b. Evaluate the function at each critical number in the open interval from a to b. Also evaluate at the function at each endpoint on the closed interval from a to b. The result of the least of these calculations will be the minimum for the function. And the largest result from the calculation of these from this function will be the maximum of the function. Okay, so let's take a look at how one's going to work here. Find the extrema of f of x equals 3x to the fourth minus 4x cubed on the closed interval from -1 to +2. First thing we need to know is what is the derivative of our function. Well, this one's pretty straightforward. F prime of x equals 12x cubed minus 12x squared. Next, we will need to know all of the x values for which the derivative could possibly equal 0 or become undefined. In order to do this, I think we need to figure out where the possible zeros are at. It should be readily obvious that there is no possibility of it becoming undefined. So what we need to do is we need to set our derivative equal to 0 and determine what all possible values could cause it to equal 0. Now, I think most of you are probably on to it already. However, this is the step-by-step procedure to which it would be done. Okay, factor out what they have in common, which is a 12x squared. And then we have the zero factor theorem. If 12x squared times x minus 1 equals 0, either the 12x squared is a 0, or the x minus 1 is a 0, or possibly both. So we set them both equal to 0 and solve each individually. On the left side, obviously, we have a possibility that x is 0, which I think most people could see right off the bat. And perhaps you might not have seen this one coming, which is why it's not a bad idea to always solve these, is that x could also equal 1, and that would zero the theorem, or the function out. Okay, so we have a couple of critical values here. Now, there are no values for x that will cause the derivative to become undefined because it does not contain a denominator of any kind. So these two locations, x equals 0 and x equals 1, are the only critical values. Okay, we also need to consider the endpoints for the function. Okay, the endpoint of one of the intervals was at -1. So we're going to take the function and we're going to evaluate it at -1. Simplifying the function, we're going to find at -1 the function's value is 7. At the other endpoint, which is 2, evaluating the function at 2 and simplifying, we're going to find that the function's value is 16. And we'll repeat the same process for the critical values. We've already discovered that the left endpoint has a value of 7. The first critical point that we ran across was that x would equal 0 at one of its critical values. Okay, so we're going to evaluate the function at 0. And when the function is evaluated at 0, the function's value is 0. Also, evaluating the function at the critical point 1 is going to give the function a value of -1. And we already know that at the right endpoint, the function's value is 16. These are the 4 particular locations to consider for the function when it comes down to extrema, and we are looking for the lowest point in the graph, which is at -1, so there's a minimum at 1, -1, and then the highest value in the graph is at 2, 16. So there are the extrema for this particular function. Okay, another example. I'm going to give you this one that I'm going to ask the substitute to press the pause button and see if you can't work your way through it. and then press play when y'all have the answer, and hopefully the answer I arrive at on the recording will match the answer that you have there in the classroom. Find the extrema of f of x equals 2x minus 3 times x to the 2/3 on the closed interval from -1 to 3. Substitute, please press the pause button. Give the students maybe 3 or 4 minutes worth of lead time as far as working the problem. When they are mostly completed, go ahead and press the play button and let the video run. Okay, the derivative of the function f would be 2 minus 2 over x to the 1/3 power. Simplifying a little bit, we have 2 times x to the 1/3 power minus 2 over x to the 1/3. Two critical numbers in there. One would be when x is 1, the derivative would be equal to 0. So we would have a horizontal tangent line there. And since we have a rational function, we also have the possibility of a vertical tangent line. And clearly that would happen when x equals 0. The derivative would be undefined. So considering these two values in the domain, 0 and 1, and also the endpoints of the interval at -1 and 3, you should have had a chart that looks something like this. When f is at -1, evaluating the function, we get a value of -5. We also have a critical point at 0. It was determined that the critical point 0 is going to give a function value 0. Critical point of 1 is going to give a function value of -1. And at the right endpoint, when you evaluate the function at 3, we get an irrational number, but it is somewhere in the ballpark of -1/4, -0.24. Okay, so evaluating those values that we have there, we have a minimum value at -1, -5, and a maximum value at 0. Now, if you're wondering how come the critical point f of 0 equals 0, you need to keep in mind the idea of a limit. Okay, we don't actually have a denominator of 0. We need to think about it. What happens as x approaches 0? And what you have there when your function, your derivative, is being evaluated as x approaches 0, we have a numerator that is becoming 0 faster than a denominator that is becoming 0. So essentially, since the denominator is exceeding the numerator's value, then you have a fraction that is approaching 0. That's how come you have f of 0 equals 0. The assignment for this day is on page 167. The numbers are 11 through 14, 17, 18, 26, and 27. Since I am not there today to answer any questions or clear up any confusion that you may have, I do intend to give you Tuesday in class in order to work on this assignment and then have the assignment due at the beginning of class on Wednesday. So you may begin the assignment at this point if you have time to do so, and if not, you can certainly continue or begin it in class on Tuesday.